Professor Kadir Babu sir. So thank you, Santapananchi sir. Thank you. So we are very much regretting for the morning session. It was delayed due to some unavoidable problems. So we are sorry for that. And one more thing, one more session by Dr. Nagamani. So due to her health issues, she is not able to come for that. She was planned online, and again she shifted, he changed her plan to online. It was offline and then online. Still she is not getting well, so that was cancelled. So so that session stands cancelled. So I'm sorry for that also. And the afternoon session will be started parallelly at 2:15. Have your lunch. It will be provided at Foodies. You can ask anyone to reach Foodies. They will direct you, right? So Foodies, you can have your lunch and then come back in the same venue. And those who are wanted to attend the lecture in Ambedkar Auditorium, so there also you can go. Parallelly, it will be conducted. Okay, so Ambedkar Auditorium and then Comrade Auditorium. So this is Ambedkar Auditorium, and 7th floor there is an auditorium named Comrade Auditorium. So you can attend these two sessions parallelly. Okay. So yeah, any queries? Okay. Okay. Shall we take a move to lunch? Okay. Thanks a lot.
Very good afternoon to all of you. I am very much delighted to introduce Dr. Don Moisam. He is a professor and head, Department of Mathematical Sciences, IIT, Varanasi. He has completed his PhD degree from IIT, Varanasi. He was the head of the department at Assam Central University. His research interests include function analysis, optimization, and mathematical modeling, fuzzy set theory, soft computing, and image processing. So far, he has successfully guided 18 PhD students and published more than 100 research papers in reputed international journals, proceedings, and edited books. His paper includes metric, fixed point theory, optimization modeling, and recently on applied analysis, soft computing, and fuzzy geometry. He has completed a BRNS BARC funded project titled Fractional Calculus Approached Solutions for Two-Dimensional Groundwater Contaminations in Unsaturated Media during 2014-18, jointly with Professor S. Dosh of IIT. Professor Jam is editor of International Journal of Fuzzy Computation and Modeling since 2018, and an editorial board member and a reviewer of several reputed journals, including IEEE Transactions, American Mathematical Society. He has jointly edited along with Professor Ghosh, Professor Giri, Professor Ram and Professor Mohapatra, Professor Sakurai and Professor Savas, the Proceedings Mathematics and Computing. Selected contributions include fixed point theory and soft computing. He has delivered several invited talks at national and international conferences, seminars and refresher courses, and has organized 4 international events as the main convener. He holds the Vice President position of Calcutta Mathematical Society. He has made short academic visits to Texas University, Kingsville, and the University of California, Berkeley. Such an eminent personality is with us. Professor is going to deliver the invited talk on I think connected with fractional calculus. Please enjoy the lecture, and after that, please interact with the professor. On behalf of the organizing committee, I welcome the professor and hand over the session to professor. Thank you.
So first of all, let me thank the organizers particularly, and for inviting me for a talk. Of course, the title of this conference is Mathematical Analysis of Fractals and then Dynamical Systems. The fractals, which of course it is delivered morning, 2 lectures, these are all based on contractions. Okay. So that is nothing but Banach contraction or other generalized contractions. So today I am just going to talk something on contractions. Contraction means we get a fixed point, or maybe if I have more than one mapping, I will get a common fixed point. So, what are the different criteria to get a fixed or common fixed point we have discussed here. So Banach established in 2022 the famous Banach contraction principle based on the condition, yes, that is this one, d of Sx_Sy less than equal to alpha dxy, where alpha lies between 0 and 1, less than 1 certainly. And this has a unique fixed point provided the space is complete. And the sequence of iterates Snx, okay, it actually converges to the fixed point of the mapping S. Later on, there are many generalization of this principle, I think more than we can count. Of course, there are plenty of generalizations as a single mapping and also for common fixed point. Okay, there are two things, either you have to go for say different spaces or the condition itself. If I change the condition, then we may have different, okay, this is the mapping condition. If there is a change, we will get a different structure. Okay. So here next one, that Picard operator, the operator S from x to x is called a Picard operator. If I take the fixed point set of S, I get something like this, Sx is equal to x, and that is, suppose x star is that fixed point here, then it must be equal to x. And this sequence is actually converging to x star as n tends to infinity. This is Picard operator. Now this is called a weakly Picard operator if the sequence Snx converges. I am not saying converges to x star, it converges, okay. And the limit, which may depend on x, choosing the initial point, is again a fixed point of S, okay. Then S is said to be some generalization I am going to. Of course, there are many other generalization which has, if you have gone through that fixed point theory, there are many, but these are some new concepts here. So this is now psi weakly Picard operator if S is weakly Picard operator, and psi is a mapping from R plus to R plus which is increasing, continuous at 0, and psi 0 is equal to 0. And d of, if I take this separation for a large number of times, it is less than equal to psi of d of x Sx for all x belonging to the set X. In particular, if S is a Picard operator, x star in X denotes the unique fixed point, then S is said to be psi Picard operator if the distance between any other point and x star is always less than equal to psi times d x Sx, okay. And now if I take psi t is equal to say constant time t, then we say that this is a C weakly Picard operator and a C weakly operator respectively, okay. And there is an example, say for any mapping, if I take the Banach contraction, then that contraction is 1 by 1 minus alpha Picard operator. You can see it in the papers of, okay, there are references, okay. Now this is again another type of contraction given by Siric in 1971, that is quasi contraction satisfying d of Sx_Sy less than equal to q max. Okay, this is structure you know if you have gone through some fixed point results, okay. X Sx x like this, okay. Now there is a very recent question in 1922 by Petrusel, that is Mihit, Mott and Petrusel, whether if I have two quasi contraction operators whether I have a common fixed point or not. He proved for one mapping, but he was not able to give a result for a common fixed point. So we are going to get some common fixed point for such mapping quasi contractions. Okay. Then we will show that there exists a unique result on common fixed point is established by on how this common fixed point is going to have some impact on stability analysis of some mathematical model. Okay. And it is going to satisfy the condition, or under which condition I can get a common fixed point for which, or a problem which is well posed, or is satisfied Ulam has stability or Ostrowski's property. Then we will use again a fixed point result, some fixed point results which for a tupling, just like say coupled fixed point you have heard about, we have tupled, n tupled fixed point, something like that. And these m tuple, I have a class of such functions, and we will show the existence of m tuple fixed point, okay, on m subsets. Given a set, I get m number of subsets, and from which we generate a m tuple fixed point on a metric space. And this is again have some application on say coupled mapping, m tupled fixed point result, and that is cyclic mapping going to have some property, such type of property, and including proximity problem, application in proximity problems. Well, I will not be able to, maybe let me come to some preliminary concepts here. Partial order set you might be knowing. Let X, this is a partial order and this is a mapping now in m tuple, okay. X, it is not power m, it is x cross m, m times. The map F is said to be mixed, said to have a mixed monotone property with respect to the index I, such that whenever x1i, x2i, okay, the ith position, say if I take two sets of m number of points, okay, only this is less than equal to this, then this f of at ith position this is less than equal to I2, okay, x1i and x2i, okay. Similarly, one side it is, this is monotonically increasing, whereas it is monotonically decreasing, okay, because this is x2 here, this is x1 here, okay. Well, Boyd or Wong, that is also in 1965, during that time defined, gave a fixed point result that is called Boyd and Wong fixed point result, that was based on a function phi, class of function phi. This is small phi contains in this class, which is from, of course, r plus to r plus, which satisfy following three conditions, very well known result, okay. Psi is upper semi-continuous from right, psi t is less than t, and psi 0 is equal to 0 always. Then based on that, that is called Boyd and Wong contraction, and based on that we have some graphic contraction where the mapping is going to satisfy. We say that this mapping is a graphic K contraction if d of Sx s square x twice less than equal to k times d of x Sx. This is called a graphic contraction. It is okay. It is also going to have some more applications there. So on graphic contraction we have the following result. Let XD be a complete metric space with a closed graph, S is having a closed graph. Then the graphic K contraction, S is graphic then if S is a graphic contraction, do we have the following implication, that Picard operators, Picard sequence S always converge to the fixed point x star, and S is 1 by 1 minus k weakly Picard operator, and the fixed point set of S is nothing but, given by this, satisfy well posed condition, okay, of Rayk-Janowski, that is, okay, fix S is equal to x star, and for any sequence Vn in X with, suppose Vn S and V is tending to 0, as n implies that Vn goes to x star as n tends to infinity. So this is well Poisnet's condition of a model, okay, and if fixed point of S which given by this has this stability property, that is nothing but for any c greater than 0, there exists some constant c greater than 0 such that for all epsilon greater than 0 and for all x bar, x tilde in X satisfying, okay, the image x bar, x tilde and Sx bar is less than, we are able to make it to be bounded by epsilon, okay, implies that d of x tilde and x star less than c times epsilon. Here x star is a fixed point and x tilde is a solution. So one is the solution, one is the fixed point. I am able to make it less than equal to c times epsilon. So this is that we are able to get a solution of a model based on some fixed point result. Now we have some beta quasi contraction, that S, the operator x to x, again fixed point set is nothing but non-empty and having at least one member x star. Then S is called a beta quasi contraction if there exists a beta in 0 1 such that d of Sx x star can be made less than beta times this, okay. So this is called beta quasi contraction. For this particular beta quasi contraction, we have the following result. Let S from x to x be a beta quasi contraction on a metric space such that if there exists a fixed point of S, then S has certain, S will satisfy, that fixed point will satisfy that this property, Ostrowski stability property, okay, what we have just shown in the last slide. So ultimately this is going to satisfy some stability problem of a model, okay. Now we have some other results here. Now I have two operators S and T, complete metric space, okay, self mapping, and now since we are taking two mappings, we have to restrict to this value alpha, which lies between 0 to 1 by 3 open map, open interval 0 to 1 by 3. And suppose SXT satisfy, ST satisfy, okay, this is a steric contraction, okay, then the following conclusions hold, that common fixed point of ST is same as fixed point set of S is equal to fixed point set of T, and that is nothing but x star. And for all x naught belonging to X, the sequence Xn given by, now alternatively it is iterated by S and T, okay, converges to x star. And for any y naught belonging to X, the sequence y given by, again that alternatively for even points T of y2n is equal to y2n plus 1, S of y2n plus 1 is equal to y2n plus 1, converges to x star. So these are the results here for common fixed point. Some examples what we have here, okay. So I take not from r plus to r plus, so I take an interval 0 to 2 to 0 to 2, and I take the mapping Sx equal to x by 10 when x lies between 0 to 1, or for x greater than 1 x by 5 and Ty is equal to this. Then this particular, remember that this is a quasi contraction, it is not a Banach contraction for some value of x and y. If I take x is equal to very close to 1, y is also very close to 1, then this is this much and y dxy is this. Therefore, if that means actually I require alpha value this to satisfy this. So and therefore this does not satisfy Banach contraction, okay, for Banach contraction less than 1. So, but it satisfies the quasi contraction, but okay. So, what we get that if we choose alpha to be 3 point, okay, within this interval, okay, 3 by 10 and 1 by 3, then the operators satisfy the relation, that is the quasi contraction what we have defined, and therefore, by our result we conclude that S2 have a, these two mappings have a common fixed point. Okay, if I just relation 3, that was the relation, okay, this is the quasi contraction. So, our result actually generalizes the Banach contraction in that sense. Now, what we have, this is a m tupled fixed point. This was a common fixed point, the earlier result. Now, if I have a space x cross m times, then what, how to get a fixed point, whether we get a fixed point or not. So, what will be the condition? Now, this is a partial order defined on this metric space X. F is a mapping from x to the power m to m, satisfies monotone property, and there suppose there exists that phi function, okay, and ultimately I have a condition here d of these are nothing but I to I minus 1 m times, okay. These are nothing but how these points are taken. Let me, you might be little bit confused whether this is I then I minus 1, what is that? It is nothing but, okay, say this is your x1, x2, x3, this is xi, xi minus 1, okay. So, here I have xm, so say this is xk, something like this. So, if I am starting with x1, this m tuple, what it means? x1, x2, x3, I have to take all the points up to xm. It is not necessary that every time I will start from x1. I can start from my initial point, that m number of tuples may start from any point. So, if I start from xi, it will take all this point continuously and it will end at here. That is the thing here, okay, xi to xi minus 1. It is not the power, it is that position, okay. Similarly, yi to yi minus 1, this is going to satisfy phi times d of xy and something like this. And suppose I have similarly, there exists some point, say x0 initial point, this is the initialization that satisfy that this is less than equal to this, okay, and this is okay. When it is odd, xi0 is less than equal to this, because you see all these things is going to x. So, ultimately it is a member in x. So, this is xi is less than equal to this. Similarly, this is now partial order, this is less than equal to even odd like this. Then what is going to happen? And suppose that x satisfies following two condition, that xn is increasing and going tending to x, okay. If xn is less than equal to x and xn is okay decreasing to, finally decreasing and decreases to x when x is less than xn. So, in that case, if these conditions are there, then I have a m tupled fixed point, okay, there exists a m tupled fixed point. Now, what is a cyclic mapping? Instead of taking the whole set X, we take m number of, okay, m number of subsets of X denoted by say A1, A2, AM, and initially F is a mapping from X to X. So, F maps also A1, A2, AM to X, okay. Then this mapping is called a cyclic mapping with AI. It is something like that. F of A1 is contained in A2, F of A2 is contained in A3 and go on. F of AM is contained in, if I start with A1, I have to again, this is very important. Okay, if I am taking subsets, then it is going to the next one, it is going to the next one. Okay, in that. Tupling were introduced by combining the concept of, remember, cyclic mapping with tupled mapping. So, we introduce now, next is phi tupling. What is that? So, again f is a mapping from x to the power m to x is called a phi tupling with respect to all these m number of subsets. If there exists a phi function belonging to capital phi whenever such that for all xi in, remember now this is a element in ai, yi element in next subset which satisfy this condition. Again you just see xi plus 1 m1, okay. So, this is the point from here, okay, and then it is contained in, if I am taking starting with xi, it is contained in this ai plus 1 and d of this distance, okay, these two is less than equal to phi times, this is the mapping here, okay, plus 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 then divide by m. Then what is going to happen? So, let f be a mapping from this be a non-empty set x, okay, an element is said to be a strong m tupled fixed point, okay. Now I am taking say same elements and then this is called a strong, that this is equal to x, actually it is with respect to the first element, okay. Maybe I have taken all the elements same here, so it is called a very strong m tuple fixed point. So, what is the result here? That xd is a complete metric space, these are all subsets, non-empty closed subsets, important one condition that these are closed subsets of x, and f is a mapping which is a phi tupling with respect to this a1 a2 m what we have just defined, and for some psi in, okay, capital phi, and intersection is non-empty. Remember, intersection of all these sets is non-empty. Then there exists a singleton, some x in this intersection ai such that, remember, for this x this is equal to x, and that means this x is a strong m tuple fixed point of f. So, you see this structure is going to get going to give you a m tuple fixed point. So, there is some remark here. It may be noted that if I take x0 1 in a1 x0 2 and so on x0 x0 xm, then the iterations converges to the, if I start with, okay, xn1 xn2, okay, nth position I start, so then it converges to the strong m tuple fixed one. Start with any structure, but the thing is that all the points will be same position wise, okay. And what more you have that if phi t is equal to, for example, okay, kt, where k belongs to 0 to 1 such that, okay, these are members of xm and it satisfies this inequality, then this is called a Banach type m tupling, okay, this is called a Banach type m tupling. So, that is also going to give you, if the conditions of that theorem are satisfied, we are going to have a m tuple fixed point. Now, there is one example here. D is a usual metric x and we take this is a whole set R. Now, I define like this from 0 to 1 by 2 m square, this a2m is equal to 0 to, okay, once it is going from some negative point to 0 and then 0 to positive point and defined by, my mapping is taken like this, then you are going to, it is going to satisfy that this point ultimately lies in ai. Remember, this is a member, this is a member in ultimately R, and if I check with this one, this is going to satisfy the condition of that theorem. And what we see that for any positive number ai, what I get, this summation ai is less than equal to this, and all these things here if I take phi t is equal to this, remember this whole sum is less than phi of this, and phi t is given by this whenever t lies between 0 1, t greater than 1 it is 0, which satisfy the condition of the function of the class capital phi what we have taken. Therefore, phi is a phi tupling with respect to all these subsets, and f satisfies all the conditions of the theorem which we have mentioned for m tupled fixed point, okay. And 0, ultimately this 0 is the strong m tuple fixed point, that is nothing but f 0 0 0 is equal to 0, m tuple fixed point. Now, how this is going to help in fractals, okay. So, this m tuple fixed point is going to have application in fractals. Remember that in fractals you have m iterated system. So, how much time I have, please, I will quickly go through, I will leave some of the portion. So, you already know what is iterated function system. So, I will not discuss, yeah. So, already, sorry. Iterated system is already defined by Professor, our chairman. Then next one is also defined phi. Now this is phi iterated system. Okay, a phi iterated tupling system consists of a complete metric space with m closed subsets and a finite set of phi tupling like this. Okay, denoted by the space, metric space, and this tuple. Okay, this is a phi tupling system. And then we have the Hutchinson mapping. It is a mapping from a closed, compact subset. Now these are all compact subsets, two compact subsets defined by FB is the union of Fi tilde B. Fi tilde B is nothing but Fi B, where B belongs to this. Then this is an attractor. Okay, be an iterated function system. P belongs to this is said to be an attractor if Fp is equal to Q for all Q belonging to this compact set of X, and limit of F and Q is exactly equal to P. Now let F be a mapping from, okay, m tupled, okay, be a continuous mapping on a complete metric space, and F tilde is a mapping from the closed, compact subsets of X m times m tupled, okay, to Kx defined by this, okay, where remember this Xij they belongs to Ai. Then the tuple, this one A1, A2, Am is a subset of that compact subsets m time, and is called a m tupled fractal if this F tilde of this is nothing but Ai. Okay, this is a very natural generalization of the earlier fractals, where A1, A2, Am is equal to A, then it becomes a it takes the form this one. Then now there is a strong m tupled fractal given by this if A is called, again F is a mapping from X to the power m to X, be a complete metric space, a strong m tuple fixed point if F tilde taking all A together m times is equal to A, and the you know the Hausdorff metric already, I hope. And then the following lemma provides the technique to phi tuple. Okay, so what is that? Let X be a metric space. These are all subsets of X. Then F is a mapping from X to the power m to X, be a continuous phi tupling with respect to A1, A2, Am, what we have defined. Then remember that then F tilde is a phi tuple between AK1, compact subsets of A1, A2, Am with respect to Hausdorff metric H introduced by D. And there is another lemma that let Fj, now it is nothing but a index set and is be a family of continuous phi tupling on Xm. I do not have only one, I have a family of such mappings, okay, with respect to A1, A2, Am for some. There is again if n number of such elements of capital phi, and each Fj is a monotone increasing, then the mapping Fkxn it is a mapping m times to kx defined by this, okay, is a phi tupling with respect to k1m, k2m, where phi t is now, this phi t is defined as maximum of this, okay. So then what you have, using, so actually it gives you that phi tupling here, the mapping with respect to, then this phi t can be given by, this phi t is ultimately reduced to this one, okay. So we have m tupled fractal result here. So here is that the result that be a continuous phi iterated tupling system on a compact metric space xd, where fj is a phi tupling on xm with respect to x to the, sorry, x1, x2, xm cross m times, okay, with closed subsets a1, a2, am, x and phi I is a subset in that class capital Phi, monotone increasing. Then f defined from this to this, okay, given by this, then there exists a strong m tupled fractal of f, okay. That means there exists an S which ultimately I have in this intersection, I have a single point capital S, and f s s s is equal to S, that is my fractal here. Just 2 minutes. So I am just skipping the proof. This is an example here. So now taking that larger example will be difficult. So we have taken only for two subsets here, f1, f2 from x4 to x defined by, okay. So this is from 4 x cross x cross x 4 times, okay. So if we take it like this, and a1 is a subset of this, a2 is a subset of x like this, then phi tupling system this generates a fractal. Remember, this generates a fractal. What is that fractal? It is given by, okay, we will get another example here, okay, in similar type, and actually the fractal generated is the Cantor type fractal is generated by this system, okay, exactly that Cantor like set this is. So I think there is some stability result. If my mapping satisfies this that is quasi contraction type condition, and alpha if we take, then ST has our graph contraction, this is beta contraction, and C Picard operator when C is equal to taken like this. So there is another result that it is going to that modeling problem here, that let S and T be x to x be two operators on a complete metric space as this, as that if I take alpha belonging to this satisfying this condition, then the following conclusions hold. Then whenever alpha is less than this value, then this fixed point set of S and fixed point set of T is going to satisfy the well posed condition of that problem of Reich and Jaworski model. Okay, if alpha is less than this, then fixed point of S and fixed have the Ulam stability property of that model, and if I take alpha less than 1 by 4, then S and T have Ostrowski's property. Okay, these are the application of that fixed point results, and so these are some more things which are already done. I think I have to skip because there is a so there is some altering point problem. I am not going to discuss now today. So these are some future direction are there, that we can construct a similar type of common fixed point theory in complete metric space for a pair of operators using convex contraction instead of graphic K contraction, okay. And then if we recall LK convex contraction, how when this S is called a LK convex contraction if it satisfies that L plus K is less than 1 with these two S is square X, okay, pair of, okay, that this is less than equal to this, something like this, okay, this is called LK convex contraction. Since any continuous LK convex contraction on a complete metric space is a Picard operator, okay, so there are future direction we have, we can something on this we can do. And there is another open problem here. Whether we can have pair of self operators satisfying the generalized quasi contraction, okay, or what is that generalized quasi contraction? It is given by something like this, okay. Here I have S square X also, so some more elements in the on the right hand side, that is again a generalized quasi contraction. So whether we can have the similar results for this new type of contractions. So that is all today. I think yeah, let me stop here. It has again the application in M tupled fixed point. So we have given a positive answer to the we can get that there is a M tupled fixed point here, okay. Similarly, that continuity assumption on F, whether it can be removed or not, or it may be weakened, and to get a M tupled fractal, okay. So this is another direction we can go. So with this I have to stop here. These are the references we have used. So not yet, yeah. No, just if we are taking all of them x, x, x and going to x, okay. That is why if we change these values, whether it is going to x or not, we have to check. So this is very much restricted, and that is why it is called a strong fixed point.
We have superposition of waves.
Okay.
So in the superposition of wave, the train of waves forms. So can I understand the train formation of the localization,
okay,
with the help of this kind of quasi contraction, the contraction of the wave field?
We have not tried, but since you are telling, yes, we have to get what type of wave structure you have, what type of mapping you are going to apply.
Okay.
Okay, maybe we have not yet checked that one. This is a physical problem. Okay. So you can send me the problem, then we'll see it.
Okay.
Okay. Right now I cannot say you that it is there. Okay.
Yes,
but if it satisfies that condition, if whatever mapping associated with that wave,
yes,
if that satisfies this condition, then certainly you can get some result.
Okay, so like physically what I'm understanding, like there is a field,
yeah,
which is like there is some, like it is originating from a point,
yeah,
and as well as it is contracting, but the magnitude of contraction is high, so that can be told as a quasi contraction, or
there are many contractions. Okay.
Okay.
Maybe it is a type of a particular,
okay,
different condition, it is going to converging to that point.
Okay,
so you may think it is a type of a contraction. Certainly it is a contraction.
Yes, sir.
Okay, converging to one point.
Okay, sir.
So certainly something can be explained.
Okay, thank you, sir.
Thank you. Thank you to the session chair, Dr. R. Uday Kumar, for sharing this session. Thank you so much, sir. And on behalf of the VIT and School of Advanced Sciences and Department of Mathematics and the organizing committee, so I am thanking the speaker, Dr. Tanmay Som. So has given the nice lecture to us and enlightening some fixed point results actually. Thank you so much, sir. Thank you so much. So I am requesting the head of the department to hand over our gift to the guest. It is. Thanks to the head of the department. Thank you, sir. And once again, we are thanking the speaker. Thank you so much, sir. You are coming over the long distance. Thank you so much. Then we will go for the next session. The next session is by Dr. Asit Saha from the Sikkim Manipal University. So again, I'm requesting Professor Tanmoy Som from IIT Varanasi to chair this session. Sir, please, sir, and introduce the speaker, Dr. Asit Saha.
So our next speaker is Dr. Osit Saha from Sikkim Manipal Institute of Technology, Sikkim. Dr. Saha received his MSc degree from the University of North Bengal with first class, PhD from Vishwa Bharati Shantinika. He has published more than 106 research articles in reputed journals. His research areas cover mainly bifurcation, chaotic, and multi-stability behaviors of nonlinear waves in plasmas and other nonlinear media. He has published one book entitled Dynamical Systems and Nonlinear Waves in Plasmas by CRC Press. Another book, edited book, Nonlinear Dynamics and Applications, published with Springer Proceedings. His other interest is to employ the concepts of nonlinear dynamics in different areas of physical problems. Dr. Saha has received University Medal and Kiran Chandra Bhattacharya Medal for securing distinction marks in MSc. He is also serving as editor for a reputed international journal, European Physics Journal Plus. He is also a life member of Calcutta Mathematical Society. He has received Emerging Researcher Award 2019, presented by Sikkim Manipal University 2019. He is enlisted in Stanford University top 2% most influential scientists for 2 consecutive years, 2020-21 and 22-23. So let us give a big hand to Dr. Saha. And 3 scholars have completed PhD under him. Okay, so I request Dr. Saha to
in plasma waves. What do we mean by dynamical system? Dynamical system is a system which changes with respect to time. Means we can find different type of qualitative behavior when time changes or the parameters of the systems are changing. So the qualitative behavior of a system is very important, and this qualitative behavior of a particular system can be analyzed by the theory of dynamical systems. In this topic, I will be discussing 2 approaches, like to study nonlinear waves with arbitrary amplitude and small amplitude. So it is nothing but a applications of theory of dynamical systems in case of plasma waves. These are the outlines of my presentation. First I will talk about dynamical system, then I will talk about phase plane analysis, we can say phase portrait analysis, then I will share some information about plasmas, and then different type of waves in plasmas. So one important wave I will be discussing, that is called super nonlinear wave. In general, we study different type of nonlinear as well as linear type of waves, but super nonlinear wave is a particular wave which is nonlinear and characterized by non-trivial topology of the phase portrait. So what do we mean by non-trivial topology of the phase portrait? If we have a phase portrait and it contains like more than 2 equilibrium points and 1 separatrix layer, then that type of phase portrait is called, means that type of geometry is called characteristic by non-trivial geometry. So we have dynamical system which changes with respect to time. We can give some few examples like flow of water in the canal or flow, different type of flow. Bifurcation is nothing but qualitative changes in a system when the parameters of values of the parameters are changing. Like what type of qualitative changes, like the system may have some equilibrium points. The equilibrium points may be created or destroyed, or their equilibrium, their stability of the equilibrium points may be changed, like stable to unstable, unstable to stable, like this. So this type of qualitative changes of a system we say as bifurcation, and the values of the parameters at which this type of qualitative behavior, qualitative changes occur are called bifurcation point. So to discuss different type of features of the nonlinear waves, first we consider phase plane analysis with linear system. So system 1 is nothing but a pair of differential equations. Dot means dx dt, y dot dy dt. So we can express this system in terms of matrix form like this, where A is the coefficient matrix, X is the variable matrix. We can find the characteristic equations, and then also we can find the eigenvalues. Now depending on the behavior, depending on the eigenvalues, we can discuss the features of the wave that is described by the system 1. Like if we can find the determinant value as well as the discriminant, and depending on this conditions we can discuss, or we can find the different type of equilibrium points. Like one point, it will be node if this condition satisfied, then spiral, then saddle, then degenerate nodes, and it this type of equilibrium point may be stable or unstable. That will be maintained by the trace of the matrix. Now without this, means instead of this condition, we can analyze in a very simple way based on the eigenvalues of the matrix. So if the eigenvalues are real and distinct, means one positive, one distinct, obviously distinct, and one positive, one negative, then the equilibrium point will be saddle point. If we have both positive eigenvalues, then we have unstable node. Similarly, if both are negative, then we have stable node. Now eigenvalues may be real or repeated, then we will get unstable star node and stable star node based on this condition. And we have, if we have eigenvalues which are complex in the form of like alpha plus minus I beta. So in this case we will be getting unstable spiral if the real part alpha is positive, and unstable spiral if alpha is negative. So based on the real part and imaginary part, we can identify the oscillation is like unstable or stable. In case of center, it will be the alpha equal to 0. Yes, sir. Eigenvalues are complex. We are finding the eigenvalues of the matrix A. Yes, yes, sir. Coefficient matrix that we have taken. Okay. Number of variables. Yeah, we have two equations. In equation 1 we have taken two equations. Then we have expressed in terms of matrix form, Ax equal to beta if, and then we have taken the coefficients A, and then we are finding the characteristic equation as well as the eigenvalues. Now we are talking about nonlinear system. So we have nonlinear system is given by equation 4. So in this case we are we are trying to apply the phase plan analysis. To do that, we are considering one equilibrium point, say x star y star and an equilibrium point. Now we are considering a small disturbance about the equilibrium points, and that disturbance is denoted by this u and v, and then using this disturbance we apply this u and v in equation 4 and applying the Taylor series expansion, and finally we can consider the first order differentiation and we can express it as matrix A, and is nothing but the Jacobian matrix at the equilibrium point. And based on the determined value of the matrix, we can and trace, we can analyze the system 4. So if we have trace of the matrix is 0, then depending on the determined value we can analyze the system. the system will be, the equilibrium point will be saddle point if we have delta less than 0, center delta greater than 0 and equal to 0, then it will be nothing but a cusp. So now we will be applying this theory of planar dynamical system in so what do we mean by plasma? Plasma is a collection of quasi-neutral gas with charged particles, and we know that 99% of the matter in the universe is in plasma state. Some examples I have given, and I will talk about super nonlinear waves. So super nonlinear wave is a particular type of nonlinear wave which is characterized by non-trivial topology of the phase portraits. And super nonlinear waves is introduced by two scientists, Dominov and his collaborator Kolokov. So in this case, we consider some notation like SNPT Mn. So SNPT, super nonlinear periodic trajectory, M number of equilibrium points in the phase portraits, N is the number of separatrix layer. So in this way, SNHT also we can consider the notation. SNHT we can consider the notation for the super nonlinear homoclinic trajectory. So based on this super nonlinear homoclinic trajectory and super nonlinear periodic trajectory, we can have super soliton and super periodic nonlinear waves. So I have given some means I have considered some phase portrait. So this is one of the example of a phase portrait where three equilibrium points are there, P0, P1, P2, and we have a pair of homoclinic orbit. So for this homoclinic orbit we can find solitary wave solution, one with positive amplitude, one with negative amplitude. So this type of positive amplitude solitary wave is called compressive solitary wave, and negative type is called rearfective solitary wave. Now we have P1 equilibrium point, and about the P1 equilibrium point we have a family of periodic orbits. For this family of periodic orbits we can find a family of periodic wave solution. Similarly in this case also we can find a family of periodic wave solution. But one type of nonlinear periodic orbit which is different from this type of family of periodic orbit, which is nothing but this. And in this case we can see three equilibrium points. It covers three equilibrium points and also one separatrix layer. So this type of orbit is called super nonlinear periodic trajectory per orbit. Here 3 means three equilibrium points, 1 means one separatrix layer. So this is one example. We can consider this type of example. In the first case we can see only super nonlinear periodic trajectory is there, but in this case super nonlinear homoclinic trajectory is also present. If we see this purple one, you can see this is a homoclinic orbit containing one separatrix layer and also three equilibrium points. So this type of super nonlinear homoclinic trajectory will give super nonlinear solitary wave solution. So this is one of the example. M number of equilibrium points. Yes, M, first one. This is Z actually. Yeah, phi Z. If we consider two variables, just I have taken example of the phase portrait. In from a system, I will show you the particular phase portrait which will be connected with the system variables. Fine. So this is another kind of phase portrait. Here we can see one separatrix layer is here, another separatrix layer is here. So we have homoclinic trajectory like this. So this homoclinic trajectory contains 5 equilibrium points, 2 separatrix layer, and also here we have super nonlinear periodic trajectory. This is one super nonlinear green one, super nonlinear periodic trajectory with 3 equilibrium points. Here another super nonlinear periodic trajectory with 5 equilibrium points. So in this way, depending on the number of equilibrium points of a nonlinear system, we can find different type of super nonlinear trajectory. It may be homoclinic type, it may be periodic type, or it may be heteroclinic type. We can consider this type of another example. So, this is the graph of the super soliton, or we can say super nonlinear solitary wave, and this work is done by Varist and his collaborator. This is super soliton. You can say super solitary wave solution, super nonlinear solitary wave solution. I will show another one. This one is the super nonlinear waves. Singh and Lakhina, they have obtained. Now, based on this work, I will show you some results where we have applied dynamical systems to find the different type of nonlinear waves in non-extensive plasma. So, we have a system of equations, we can say model equations, we can say basic equations. In this case, we are considering ion acoustic wave. Ion acoustic wave means we are considering the dynamics of ions only. That is why the wave is called ion acoustic wave. And first equation is the equation of continuity. Then second one is equation of momentum balance. Third one is the nothing but Poisson equations. Here the coefficients are given. Alpha is the nothing but the ratio. Q is non-extensive parameter. Sigma is the ratio, temperature ratio of cold electron and hot electron. So, we have cold electron NC, number density of cold electrons, NH, number density of hot electrons, Ni, number density of ions. Phi is the electrostatic potential, Ui is the velocity of ions, Ni, number density of ions. And in this case, NH follow Q non-extensive distribution. This is the form of the distribution. There are different kind of distribution. Here cold electrons follow Maxwell distribution. Sigma is nothing but the temperature ratio. So, we will be applying theory of planar dynamical systems in this plasma system. So, we are considering one travelling wave transformation like given is J equal to x minus Vt. V is the speed of the travelling wave, and if we consider the direction, then we can also say it is velocity of the travelling wave. And using this transformation into the main equations 1, 2, 3, we can find one differential equation in this form. So, applying the Taylor series expansion, we can obtain a dynamical system of, we can say, second order differential equation, and from that A, B, C are ABCD are the nothing but the coefficients we can see. Just if we simplify, we will get this form. This is a very simple differential equation we can see. Now, we can convert it into a planar dynamical system like this, very simple, like we have x dot, y dot. So, we have the system in this form. Now, we can find the equilibrium points. So, equilibrium points are points where there is no flow, no motion. So, obviously, d phi, dj and dz, dzi will be 0, and we can solve it, we can find the equilibrium points. So, in this way we can find, and the equilibrium points are like this. So, depending on these conditions, we have 2 equilibrium points, and if you consider another condition, then we have 4 equilibrium points. We are denoting the equilibrium points by E naught, E1, E2, E3 in this way. Now, we can calculate the determinant value of the Jacobian matrix that we denote it by J, and if J is less than 0, we have seen that the trace of the matrix is 0 in this case. If determinant value is less than 0, then it is a saddle point. If it is greater than 0, then it will be a center. In this case, cusp condition is not coming, that is why I have not mentioned. So, these are the 3 phase portraits of the dynamical system considering this parameters value. Here Q is not parameter, so it ranges from -1 to plus infinity. I have chosen 3 particular values in different ranges. So, in this case we have 2 equilibrium points, family of periodic orbits, homoclinic orbit, same type of, but if we see, this one is the center here, this one is the center, but little bit different type, and here if we can see that saddle point is nothing but center. So, depending on the values of the parameter, now the shape of the phase portrait is changing, and ultimately you can see there the here center is the origin is the center, but here origin is the saddle point. So, in this way, for different values of the parameter we can find different type of phase portraits, and based on the phase portraits we can find different type of nonlinear wave solutions. So, this is one of the phase portrait with periodic orbits, homoclinic orbits, and also super nonlinear periodic orbits, or we can say trajectory. So, this is the homoclinic orbit. This is the homoclinic orbit, super nonlinear homoclinic orbit, containing 3 equilibrium points and 1 separatrix layer. Super nonlinear periodic trajectory is also there. That blue one is the super nonlinear periodic trajectory. This is another phase portrait, just changing the values of the parameter q, other values are I think same. So, same type. If we consider the value of the parameter q as 1.3, then we are getting this type of phase portrait. So, in this case we can see there is no super nonlinear periodic trajectory. So, there are equilibrium points 1, 2, 3, 4, but there is no super nonlinear type of orbit. So, for this super nonlinear periodic trajectory, we have this periodic wave solution. We have the super periodic wave solution like this, but this is nothing but the solution, periodic wave solution corresponding to periodic trajectory. So, we have shown 2 phase portraits based on this. First one is for figure 9, second one for figure 10. This is also super periodic trajectory. So, from a particular plasma system, we can analyze by applying the theory of planar dynamical system different kind of nonlinear wave features. Now, I will talk about multiperiodic chaotic phenomena of nonlinear waves in plasma. So, for this we consider one particular system. So, these are the basic equations. In this case, our system is magnetized plasma. So, magnetic effect is there. First one is the equation of continuity, second one is the equation of momentum balance, and this is the effect due to magnetic field, and here electrons are q non-extensive types, and n is the number density of ions. I have shown some information regarding the normalization. Now, we will consider stretching. So, stretching to find the nonlinear evolution equation. We have a system of basic equations. Now, to find the nonlinear evolution equations, we need some stretching as well as we need some expansion of the dependent variables. So, we have the stretching like this. So, for a Kp type equation, we have this type of stretching. Epsilon is the strength of the nonlinearity. V is the phase velocity of the ionocaustic waves. So, we have expansion of the dependent variables are like this. So, based on this expansion and the stretching, we can find the nonlinear evolution equation that is of the type Kp type. So, using this expansion and the stretching and removing all higher power terms, we can obtain nonlinear evolution equations of the Kp type. This is Kp type equation. Why it is called Kp type? If we remove this term, then it becomes Kp equation. That is why it is called Kp type equation. Now, we can find a different type of nonlinear wave features for this equation. So, we will consider transformation like this. Here 3 dimensions. So, we can see the variables are zeta, eta, xi. So, we have taken direction cosines this, and these are the direction cosines of the line of wave propagations. So, this condition will be satisfied, use nothing but the travelling wave velocity. So, using this transformation in the Kp type equation, we can form a dynamical system like this. So, we have 4-dimensional dynamical system. 4-dimensional dynamical system. Here the coefficients alpha, beta, gamma, delta are given by this. Now we want to analyze this to find different type of nonlinear wave features. So to do that, first we need to find the equilibrium points where there is no flow. So we are finding two equilibrium points. If we solve those system of equations considering first derivative equal to 0, and if we have a system of equations and if we solve it, then we will get 2 points. One point is E naught, another point is E1, and for these 2 points we can find the corresponding Jacobian matrix. So Jacobian matrix for E naught and E1 are given by this. So if we have Jacobian matrix, then we can find the eigenvalues. Now depending on the eigenvalues, we can analyze the type of the equilibrium point. Here E naught is unstable and E1 is stable. In case of E1, it is we are getting the eigenvalues which are purely imaginary, and here eigenvalues are opposite sign. So we have unstable equilibrium point. So these are the phase portraits considering particular values of the parameter with different initial condition. I will show you what are the initial condition for this. Space is not there, that is why I have not shown here. So the behavior of the dynamical system are like this. Different type of phase portraits we can see. First one, we can see the orbits really we can't understand what type of orbit is there. It is a irregular type, right? Irregular type. But you can see, yes, some pattern we can see. So this is nothing but multi-periodic type of solution. This one is quasi-periodic. This one is also quasi-periodic. This one is also quadriperiodic. Now this we can see it is one periodic, another one periodic, and total is another periodic. So total we can say 3 periodic, period 3 type of solution. So these are the features of the dynamical system considering only these values of the parameter with different initial conditions. What are the conditions that I will show you in the next slide, means after next slide. So considering same values, other initial conditions, we are having also this type of phase portraits. This type of phase portraits, and depending on the first phase portrait, what will be the Lyapunov exponents, that I have shown here this in figure J. So we can see the Lyapunov exponents are positive, like U. With respect to U, we have plotted the Lyapunov exponents. Our system was 4-dimensional, so there are, we can see 4 Lyapunov curves are there. So and if we see the first figure, then what is the value of U? Value of U is nothing but 0.18. So for the 0.18, we have this phase portraits. So what is the corresponding Lyapunov exponent for 0.18? So for 0.18, we can see these are the Lyapunov exponents. Which one is maximum Lyapunov exponent? Largest one this, and this is positive. So our nature is, the feature is chaotic type. These are the initial conditions. We have figures 14 A, B, C, D, E, F, G, H, I, and 15J. 15J is nothing but Lyapunov exponent. Curve of Lyapunov exponent we have shown, and these are the initial conditions. But the parameter values of the parameters are same. First one chaotic, then multi-periodic, then quasi. Period 3 that I have shown, again quasi-periodic, periodic 2, period 1. That this is period 1. This is period 1, but this one is period 2. So in this way, considering a simple plasma system, we can apply dynamical system not only for 2 dimension, maybe for higher dimension, like here we have 4-dimensional dynamical system, and 4-dimensional dynamical system, and using particular values of the parameter with different initial conditions, we have different type of features. We have not changed the value of the parameters. Parameter values are same, just initial conditions are changed. You can see the initial conditions. These are the initial conditions. P naught, just we have taken the initial value, that is why just P naught we have mentioned. So, these are the different type of features for the plasma system. So, what we are getting? Super nonlinear periodic trajectories we are having. Those trajectories correspond to super nonlinear periodic wave solution. We are having super nonlinear homoclinic trajectories. Those super nonlinear homoclinic trajectories correspond super solitons, or we can say super nonlinear solitary wave solutions, and nonlinear homoclinic trajectory corresponds solitons or solitary waves. Multiperiodic, quasi-periodic and chaotic phenomena we have seen. So, these are the conclusion points. Some references I have shown, not all. These are the references. These are my scholars. First one is my postdoc research fellow Dr. Jeet Sarkar. 3 my scholars, Jharna Tamang, Rustam Ali, Poonam Kumari Posar. They have obtained their degree, PhD degree, and 5 scholars, their research work, PhD work are going on. First one, Varsha Pradhan, she has already submitted the thesis and review reports have come, and her defense is on 4th September. Maybe he will be getting the degree on 4th September. In February 2024, we will be organizing International Conference on Nonlinear Dynamics and Applications at Sikkim Manipal Institute of Technology, Sikkim Manipal University. Myself and Professor Shanto Banerjee are the organizing secretary. You can Google, just you can use ICNDA, you will get all information. So, this is the website we have, icnda.in. Our proceedings will be published by Springer Physics, Scopus indexed, and registration paper submissions are open. You can have a look. Thank you very much for your patience. If you have any query, please, I will be happy to, yes. Yes.
So, in the case of super soliton, what kind of collision will be observed? It will be still the perfectly elastic, or you see something extraordinary?
Yeah, perfectly elastic.
Because we know that something like beam wave comes from nowhere and forms the collision. So, I am seeing some signature of that kind of, if there are 2 super soliton and they are colliding, and it can lead to
interaction.
some kind of
Interaction is there. Actually, that interaction will be there, and after interaction their phase will be changed. After interaction their phase will be changed. In case of soliton, they retain their shape and feature, but phase will be changed.
At the time of collision, there also we see a sudden change, but I don't know. Will there be a change in the
when 2 solitons will collide, then it will be a single soliton.
At the instant.
Yeah. At a, suppose if we consider a symmetric system, like one approaching from negative side, another approaching from positive side. So, if it is symmetric, then at say t equal to 0, they will collide. When they will collide, they will make a single soliton, and after collision, they will move in their direction, separating them, and their phase will be changed. But in case of super periodic waves, I have not studied the interaction, but the interaction will be there.
So, these are ion acoustic wave only, or it could be electromagnetic wave also?
Any kind of wave.
It can be, but it is modeled for ion acoustic wave, right?
Yeah, this plasma system I have taken for ion acoustic. So, So in case of plasma, there will be different kind of waves like dust acoustic wave, positron acoustic wave, dust ion acoustic wave. So depending on the plasma particles. So electromagnetic wave also. I have studied different kind of waves like optical soliton also I have studied. I have studied also tsunami waves. So theory can be applied to different kind of waves, small amplitude as well as arbitrary amplitude.
So that's what I'm talking about, rogue wave in the
Rogue
ocean.
wave, yes, rogue wave can be, yeah.
That's what I was expecting, that if there are two super soliton and that time of collision, what we observe. So is there any kind of, because they used to stay for the at instant, and they just
when they will collide, then it becomes a new soliton just for that moment. New soliton with like high amplitude, with high amplitude.
can I
like
say that rogue soliton, that rogue behavior at that instant, when it is having a sudden amplitude?
No. Soliton behavior of the soliton will be same. Just its width and amplitude will be high, and after separation, they will retain their shape and speed, but only phase will be changed.
And another thing, like phase plane diagram you have drawn for
Yes,
anything,
yes,
sir.
yes.
So as I know, basically I used to draw the phase plane for phi and phi dot, but here I saw phi and z. I was
Z is not
Phi dot.
d phi dj. So
Phi
that
dot,
is
okay,
that is phi dot only.
Okay, sir. Okay, sir.
I have taken the notation Z. So
And
you can write phi dot, no issue.
so there I'm seeing some limit cycles also. So
These are periodic orbits.
periodic orbit.
Periodic orbits.
In the case of solitons, can I say these are the pulsating soliton from one amplitude to another amplitude? And like we having something called pulsating soliton.
Yeah.
It pulsates between two amplitudes. So the limit cycle, can it represent the pulsating soliton, which
No. This
just vibrate from A1 to A2 periodically?
periodic orbit
Yes.
represents periodic solution. Homoclinic orbit represents pulse-like soliton. Means
Okay.
soliton.
Okay, sir.
Homoclinic orbits represent soliton or solitary waves.
Okay.
Yeah. So there are multi-soliton also, like one soliton bigger type, another soliton is smaller one. Bigger soliton has what is called higher speed. So at a particular time it will cross the smaller one, and when they will be crossing, then it will be a new soliton type. But after certain time, it will means keep behind the smaller one, and the bigger one will go.
In the same phase plane, I was seeing like that the saddle, we have some node point, and then it was transforming to saddle node. So that is that the signature of saddle node bifurcation there? Like in the right hand side, we have something node.
Obviously, different type of bifurcation may be there.
Okay.
If you change the parameter and if you are getting some changes,
Yes.
then it will be bifurcation.
So those are all the like orbits are for the different parameter, right, sir? Like for one particular parameters, it has been varied, and you have obtained.
You have to consider a key parameter.
Yes.
You have to change the parameter. You can't change at a time all parameters.
Okay.
Then you can't say that for which parameter this bifurcation is occurring. You have to consider one parameter, or if you consider biparameter, then along x, along y, you have to consider two parameters at a time. Then you can also means analyze biparameter analysis. But if you analyze a system for the bifurcation point, you can consider one parameter as a key parameter, like you can plot x-axis, and then you can plot the other variable along y-axis, and you can find the bifurcation. Or you can consider different vector fields to see the different kind of vector fields with respect to the changing of the parameter.
Maybe one question is there, but after I can talk.
Yeah, you can discuss little
No
later.
problem.
I think this is all. Let us give a big hand to Dr.
Thank you.
Saha
Thank you, sir.
for a nice presentation.
Thank you all.
Sir, thank you, sir. Thank you, Professor Tanmay Som. So I am requesting Tanmay Som, sir, to stay here. So I am requesting the head of the department to hand over the memento to our Tanmay Som. So, sir, thanks for your chairing the session, sir. Thank you so much. Thank you so much, sir. And we are thanking the Asis Saga, sir, for delivering this lecture. And I'm requesting Professor Sarfa, can you please, ma'am, join to hand out this gift to Professor Aziz Saha? Back.